via measure concentration in configuration spaces. Okay, so I want to present a slight generalization of the result that June presented. That said, I'm not totally convinced that somehow what the approach I will give today will lead to some of the complete resolution. We have a new approach which somehow seems more promising. So what I want to talk about is, so let me go slowly again. So for those that visited June's talk, there will be somehow 10 to 20 minutes at the start that will be boring. Let me just talk about what are my objects, define my objects. Well, so I want to talk about matroids. So these are collections of, these are pairs of a finite set E. By the way, there are actually finite matroids as well. So von Neumann actually considered them in some works, but we will disregard them for our purpose here. A collection of subsets of E called the lattice of flats. It's called the lattice of flats. And these are designed to capture your standard intuition of what subspace arrangement, what hyperplane arrangements over some field would be. So what are the axioms that I need? So first of all, well, there are some variants on these axioms, but for me, I will always just assume that the empty set and the total set are elements in my lattice of flats. Second, the lattice of flats is closed under intersection. And then a little more complicated condition is that if I have any element in my lattice of flats, then I can define a set C of S, and this is a collection of all T without S, where T is an element in the lattice of flats, so it's a flat. So the elements here called flats, and T covers S. By which I mean T contains S, and there is no set in between, no flat in between. Okay? And what do I demand of this set? Well, this partitions the ground set, but without the set S. Okay?
So suppose I only know about matroid in terms of independent sets. Can you explain what the flat is?
Yeah. So a flat is a set of maximal rank. So a maximal set of a fixed rank. This is a better way to say it. So this means that if you have a flat, if you add any other element that is not yet in your set, then you increase the rank. That's the way to think about it. Okay. So I mean, this is one of the first exercises if you study matroid theory. There are tons of definitions, and going between them is small. Okay, so what examples could we look at here? So what June talked about is well, the examples of hyperplane range. Huh?
What do you mean?
Yeah. So these are sets, right? This is a collection of subsets of E, right? Well, actually, a collection of subsets of E without S. And this should be somehow they should first of all cover the E without S, but they also shouldn't intersect. That's the point. Okay, so let's do an example. So the first example, and this is the one that June talked about, is hyperplane arrangements. So these are just somehow, for those who were there, collections of hyperplanes in over some field. Okay. So let's see whether somehow we can figure out why these are matroids. So I usually somehow a collection of hyperplane, and this is my arrangement. So let's see why they satisfy these actions. So let's go rather slow. So what is my ground set? Well, this is my collection of hyperplanes. So now, what would be my flats? This would be this is the important thing we have to observe. You have an idea? Huh? We can take hyperplanes to the linear hyperplanes. Yeah, precisely. Actually, let's restrict to that case. If you don't have linear, then you can do some trick, but it's not important. This is what I'm asking. What would be the flats? It's a Jerusalem style seminar, so you also have to answer questions. So this is just some collection of hyperplanes you like. Okay, so it's not all hyperplanes, right? We all want a finite collection of hyperplanes. And now what would be the flats? No, what do you mean intersected with A? So one way to do it, flats could be those subspaces or collections or subsets in A that intersect in a common subspace. So for instance, the flat corresponding to the origin would be everything, right? The flat corresponding to the surrounding vector space would be nothing, right? Okay. Is it also clear why I have these actions satisfied? So the second and the third. Why is the second satisfied? Precisely, yeah. So what an intersection corresponds to taking the span of the two subspaces that I'm looking at. And the third is also equally simply verified. So these are called the realizable matroids. This is what June talked about. So these matroids. So let me write it here. Brushes in color. The matroids obtained this way are the realizable matroids. Okay. Okay. So now today I want to talk about a slightly larger class of matroids. And this is called the class of C arrangements. So C arrangements, as far as I know, so the first I heard of it, go back to Goresky MacPherson, and they are kind of a naive analog or naive way to study complex hyperplane arrangements over the reals. So a C arrangement is a collection of linear codimension C subspaces in R to the D such that each intersection has dimension divisible by C. Codimension divisible by C. Well, it actually doesn't, because I took linear. No, it actually doesn't matter. I don't take the empty set. Actually, let me leave the definition for a moment. So, examples of C arrangements. So for C equal 1, well, these are just real hyperplane arrangements. For C equals 2, so a C arrangement is a collection of codimensional C subspaces such that every intersection has a codimension divisible by C. Okay? So if we're only interested in the combinatorics, it's more equivalent to say just dimension here. But this doesn't matter. So now C arrangements with C equal 1 are just real hyperplane arrangements, right? C arrangements with C equal to 2 are. Well, example is a complex. Do you also have an example that these are not all? So if you want one example where you cannot realize of a two arrangement that you cannot realize as a complex hyperplane arrangements, what you can do, you can look at a two arrangement in R4. This you can see as an arrangement of circles in the three-sphere, right? And if you are a complex hyperplane arrangements, then the way that these circles link is given to you by the Hopf linking. Okay? If you have just a two arrangement, then it's just an arbitrary arrangement of great circles that do not intersect. And you can just figure out an example where they do not intersect in the Hopf linking way. A second way to see it is that C arrangements don't satisfy these incidents, these very classical incidence theorems like Dirac theorem and so on. And then you just find this two arrangements that does not satisfy. I think Goresky MacPherson found one that does not satisfy Pappo's arrangement, the Pappo's theorem. So here you can go further, and these are quaternionic. But now it's really somehow you just see that there is difference once you go higher. So the C arrangements for me are just a way to test whether some theorem really has an algebraic nature or there is something deeper behind it that is only combinatorial. Okay, so it's not so much that they are very exciting objects. They are just somehow they are the first step to fully combinatorialize a result. Okay. So to see the true nature behind a classical result that you would have in algebraic geometry, and I will tell several examples of this, and then I will also go and prove June's result for general C arrangements. But as I said, well, the proof you have to be careful because I don't quite believe that this is a proof that will work for all matroids in the end. But so these are small, I will just call them C matroids. And these are matroids realizable as C arrangements. Yes, C arrangements. Okay? Okay, good. So, we have the lattice of flats L. This is just a poset, and it's ranked in a natural way, right? So we have our maximal set, so the total around at the top, and then we have something at the bottom. And now you can draw the Hasse diagram corresponding to everything in between, and you will see that the height in the Hasse diagram, it gives you a well-defined rank function. So this is rank 1, this is rank 2, and so on. Okay, so this gives you a well-defined rank function. So once we have this, the nice ranking, we can define a second ingredient. And this is, if we have a poset, then we can define it. It's Möbius function. So Möbius function of the poset is always evaluated at 2 elements. And the definition is just recursively as follows. Well, so it's 0 if y is less than x. It's 1 if x is equal to y. So that was the same. This is just our induction start. And it's minus the sum. And now I have to go over x less or equal to z less than y of the Möbius function at x and z. Okay? And now I can combine these two things for ranked poset to what I call a characteristic polynomial. So I take my poset and I introduce a nice variable lambda, and I define this as the sum over the Möbius function evaluated at the minimal element. So this is somehow, for me, it's always the empty set, and the maximal element is always the total set. So this is just in notation the minimal element. And the element x, and I have to go over all x in my poset, and now I have to add a factor that it goes to the lambda to the rank of the poset minus the rank of x. Okay, so where the rank of the poset is some number, usually you just take the maximum over the rank of all elements, okay? And the rank of x varies with the element. Okay, good. And this is a polynomial, and so you can rewrite it as some polynomial with coefficients gamma I times lambda to the I, and these numbers for gamma I or for m a matroid, are called the Whitney numbers. And to be precise, the Whitney numbers of the first kind. Okay? Okay, so let's do some examples. So I have a line, I have 2 lines, I have 3 lines intersecting a point, so 1, 1, 2, 1, 2, 3. And for matroids, it will usually be standard that the rank of the matroid is just the maximum rank that I see in the poset. So the poset here would be just very boring. It would just be the minimal element and the maximal element, so anti-set and the total set. In this case, it would be a little more exciting with this. In this case, just a little more exciting with the excitingness of the examples is limited by my drawing skills here. So this is empty set. This is a total set. So 1 intersected 2 intersected 3 intersected 2, and this is 1, 2, 1, 2, 3. So let's just compute for these examples the characteristic polynomial. So what is it here? So let's first find out what the Möbius function is. 1, and then minus 1. Is it guessing because you know the characteristic polynomial or because you compute it? Okay, good. What is it here? This is 1, right? Because I sum up below and then take the negative, okay? In here, it's 1. It's minus 1 here. Okay, this is clear. And what I have here? 2. Okay. So my characteristic polynomial would be lambda minus 1, lambda square minus 2 lambda plus 1, and lambda square minus 3 lambda plus 2. Okay? So, right here. Okay. So here's a conjecture. Goes back to Rota and Heron and Welsh. And this is it. These coefficients gamma I form a log-concave sequence. By which I mean that gamma I squared is larger or equal to gamma I minus 1 times gamma I plus 1 for all r. Okay? Hmm? Yeah, I think so. Just by the recursion formula I will write on in a minute. Yeah. Hmm? Ah, yeah, okay. Sorry, yeah, it's even simpler, yeah. Okay, and this theorem is, this conjecture is a theorem for the following cases. So first, June, and then together with Eric Katz, they proved it for realizable matroids. And today I will present to you the proof for C matroids. Yeah, very obvious. They are alternating. It's a very easy exercise. So let me just note some facts that are quite useful. So there are things that are quite obvious for arrangements that make your arrangement smaller. So one is called deletion, and one is called contraction. They are visualized. So the deletion of an element, sorry, I always make this in the wrong way. The deletion of an element is just you take your arrangement and you take one element out. Okay? The contraction of an element, well, what other operation could you have? Well, if you have an arrangement and now you just restrict to one of the subspaces. It's also very easy. And then it turns out that the characteristic polynomial, it satisfies this simple recursion relation. Okay? From this, you conclude several effects just simply. So these gamma i's are alternating in sign. And the gamma I sequence has no internal zeros. Okay? And one corollary from that is, so if you have the conjecture that these gamma I form a unimodal sequence. So unimodal is kind of, it feels very, very much like the Lefschetz theorem also, but you want to just say that the gamma i's rise to some point, and then they fall down again. Okay? So there is no, it doesn't look like this. Okay. Unimodal. It means that they go up, the coefficients rise to some point, and then they fall down. So I should be careful. The absolute values of the gamma I, otherwise it doesn't make sense. Okay? But the middle is not always the same. So there is a hard Lefschetz theorem that lives behind here, but it's not quite, it doesn't quite work with these coefficients here. Okay. So let me just make some remarks why this is maybe not totally surprising. And this is somehow this history of C arrangements, which served as some of this testing ground of going beyond this classical complex algebraic geometry. So this is not totally surprising. So let me just write down some things that that might be of interest here. So something that has been studied for arrangements a lot is the complement. And so this is usually denoted by just this, or or sometimes M of A, which is a more standard notation, but which is bad for me because I already talked about matroids. The complement of A, the underlying variety of A, and it satisfies some nice properties. For instance, the homology of the complement behaves in the same for C arrangements, behaves in the same way as it does for complex hyperplane arrangements. By which I mean it's torsion free plane arrangements. It's torsion free. And it is determined just by, it's combinatorially determined. So this is a more general effect. Another thing, so for complex hyperplane, for complements of complex hyperplane arrangements, the Lefschetz theorem, the Lefschetz section theorem holds, just because you can pass to what is called the Milner fiber of the arrangement, and then apply the classical Lefschetz section theorem there, and then lift back to the complement. It turns out that that this also holds for C arrangements. A of C. So this is actually this is Goresky MacPherson. A C arrangement satisfies the Lefschetz section theorem. Yes, and then you look at the complement, and the complement restricted to this hyperplane, and then there's only a single dimension of cells that you need to attach to get from one to the other. That's the point. There is a caveat, and this has to do with the first example of a C arrangement that is not a complex hyperplane arrangement I mentioned. So a caveat, for instance, you have to be careful. The cohomology ring of the complement of a C arrangement is not combinatorially determined. So it's not the Oleg-Solomon algebra. Make clear that I want the product structure here. Is not combinatorially. Meaning that you can find two arrangements with the same, that define the same matroid, but still have different cohomology rings in the complement. Okay, so this is just a little background for this business of finding some of the true underlying nature of things. Yeah. No, you don't need to know. It's just something that somehow, if you were a June stock, you might remember that the left-shed section theorem for the complements was one crucial fact.
When you say homology combinatorial, you get just a pretty number, or that you
No, that's a problem, right? So the Betty numbers are determined, but the group, huh? No, this is the problem. This does not work for general LC arrangements. It only works for complex hyperplane arrangements.
But the Betty numbers are just the assumption.
Yeah. That's actually another good observation. Let me make that. So, what's your name again? What's your name? Ah, I thought you couldn't come. I was confused because of that. Okay. Remark is that these Betty numbers, the Betty number of the complements of, so you have to be careful. The Betty numbers, let me write the non-trivial Betty numbers. Non-trivial Betty numbers of the complements coincide up to sign with the Whitney numbers. Well, you have to be a little careful if C is larger than 1. Okay, if C is equal to 1, then it's a hyperplane arrangement, and they all fall together in one number, and it you cannot recover them. This simply, at least. Okay. So now let me give a quick how-to, and then let me go to a quick how-to, and then for the second part of the talk, I will give in the second part of the talk, I will try to sketch the proof more details. So, how to prove the theorem for theorems. So the first ingredient I want to go over is basic convex geometry. So what we want to look at is the following function. So let's say K and cannot use L. K and B are convex bodies. And actually, for simplicity, I can assume that B is a unit ball. And these live in some Euclidean space. And I want to study the function of K Minkowski sum T times the unit ball. And it turns out that this is a polynomial. So it's this is some that we call sigma I of K times Ti, T to the I. And this is called, what is the Steiner polynomial. And my goal for the proof of this, of the main theorem, is follows. So let me actually make first an observation. Observe by the Alexander-Fenchel inequalities, the sequence sigma I of k is log-concave. And now the canonical approach to my conjecture would be, or to my theorem would be, hence we want to prove that for every C arrangement there exists a convex body K such that these coefficients, actually there is a renormalization, but we'll go over this in the second part of the talk, sigma I of K coincide up to sign with the Whitney numbers of the arrangement. And finding this convex body will be done by a measure concentration. This is what I will do in the second part of the talk. But actually, so it's a little early, but let me take a break here and then we can go over the proof. So what is usual? What? 10 minutes, okay. So in 10 minutes we start again with the second part. Okay. Sorry? The sign is positive. I will show you in a minute how to interpret them. Let's start again. So let's study the Steiner polynomial for a minute, because I have to do some deformations of it, some manipulations. So let's say assume that K is a polytope. Let K be a polytope. So how does the Steiner polynomial look like, and why are the coefficients positive for this? So let's say I have my polytope here, and now I want to add t times the unit ball. So the result should look something like this. Okay, and from this you can immediately read off the coefficients. All right. So, what is sigma 0 of my convex body? Well, this is just the volume. Okay. Sigma 1. Actually, I should have written this on the other side because the formula is longer. So sigma 1 of K. Well, this is just so. What is the degree 1 coefficient? How do I see it? Well, this is some of the small. Let me first say it intuitively. This is this part here, all right? So how do I make this more precise? Well, so I could define for a face. So if tau is a face of tau is the face of the convex body of my convex polytope K, then I could define n of tau as the set of all x in my surrounding space, such that the closest point projection of x to K lies in tau. All right, so this could be, this I could call the normal cone. So n of, if this is my face A, then n of A would be this thing here. And the restriction of k plus t of B to n of A, this precisely gives me one contribution to the linear coefficient. All right, so what I want to write here is I want to write the sum over the volume of one-dimensional faces, tau one-dimensional face, volume of tau times a half. What else? Well, I should now, okay, so now I have the linear coefficient to go to the higher coefficient, so let me go directly to because I'm only on one side. So what is the general coefficient? Well, so I have to sum over tau the k faces. Then I take the volume of, or summing over the volume of the k faces times what I call the normalized angle at the face, and times the volume of the k-dimensional volume of the k-dimensional unit ball, volume k-dimensional unit ball. Let me volume of BK, where BK is the k-dimensional unit ball. And here I define this normalized angle, n of tau, in such a way. So I look at my face. Let's say this is my face tau. And now I look at region n of tau I described before, right? This normal cone. And now I take a sufficiently small ball containing around an interior point of tau. So now I define it like this. Tau is, in this case, is just a vertex. Tau is a face, okay? And I define this coefficient n of tau. And this is just, I take a small ball around this face, okay? And now I measure the portion of this ball that lies inside this normal cone n of tau, okay? So this is how I define little n of tau, okay? N of tau, and this is normalized exterior angle at tau. Okay? So this explains the coefficients. It also explains directly why all the coefficients of the Steiner polynomial are positive. And this makes it very useful. So what we know now, well, so let me recall, the coefficients sigma k are positive and log-concave. But I want to simplify this all a little by cutting out this non-combinatorial part of these coefficients of the ball corresponding to the volumes of the ball. So I want to say that I can define the coefficient sigma tilde k, where I just, so I sum still over k-dimensional faces, tau k-dimensional faces. And now I take still the volume of tau, and I still take this normalized angle, but I leave out the volume of the ball. And I claim that these coefficients are still log-concave. For this, let me look at the coefficient. It's a little simpler to look at the coefficient sigma tilde d minus k, where of the polytope k. Well, but let me actually add an index, which is k to the d, and by this I mean I take the embedding of k into Rd. Okay, so I take my convex body and I embed it into some higher dimensional space. And this is now just, well, I can just look at this as follows. Sigma, actually, this is not quite the coefficient I want. So sigma, we got sigma hat. So sigma hat of, so this I define as volume of tau, n of tau. And now the usual b of d times k, b of d minus k. And now I have to go over d minus k dimensional phases. And now I multiply with a term pi to minus d minus k over 2 times pi times d or square root times d divided by 2e to the d over 2. Okay, so I have these new coefficients here. And I claim, so this is just a renormalization of these of my original coefficient sigma, and I claim this sequence is still log-concave. Why? Well, I multiplied my original log-concave sequence just with an exponential term, which preserves log-concavity, and with a constant term, which also preserves log-concavity. So now I claim that as d goes to infinity, these terms sigma hat, they converge to the term sigma tilde, and this is just a Stirling formula. Yeah, precisely. Okay, so this is the first combinatorial realization, and it's kind of a already useful one because now we can identify for the simplest arrangements we can identify the desired convex bodies. So the idea that we want to use is we want to find the convex bodies. To find convex bodies, K of A, we rely on sonotopes and zonoids. Zonoids. Okay, so what is the simplest way to do it? Also, if I have a hyperplane arrangement, then I can draw for every element, I can draw a unit length normal, right? So like this, and now I can sum them up. It's equal to the. Now I should. This is the Minkowski sum of this segment plus this segment plus this segment. It's not quite the right drawing, but it's more or less an epsilon drawing of this. So in general, if A is an arrangement, then I map it to the zonoids Z of A, defined as the Minkowski sum over what I call the generalized normals over subspaces H and A, where n of H subspace is a unit volume disk in H perp. Okay? So now I have a way to define, to associate for to each convex body, I have to each arrangement, I have at least one convex body. So let's see whether this works out. So let me make a very simple example where we can just compute it. Let's look at this hyperplane range, right, of just two orthogonal lines. And let's look at the zonotope. So the zonotope that I would associate to this is just the square, the unit square, right? Square of unit edge lengths. So what would be the coefficient sigma tilde that I would associate to this? Oh, sigma tilde, let me write down sigma tilde 0, sigma tilde 1, sigma tilde 2. For this convex body, for this is K. Yeah. Well, so I have a unit volume. So these are unit edge lengths. So I have 1 to 1. Why? 1 is the volume. Yeah. Yeah. Okay. So in this simple case, it works out. And it is quite useful to observe at this point that there is already a kind of flavor of deletion contraction to this kind of volume computation. So let's recall before we go to the problem with this approach. Let's recall the following fact. So recall, the characteristic polynomial satisfies the following relation, which was P of the characteristic polynomial of the matroid is the characteristic polynomial of the deletion minus the characteristic polynomial of the contraction. Okay, and this gives an obvious recursion formula for the Whitney numbers of the matroid. Okay, so I want to observe that up to a caveat, there is the same phenomenon that in the computation of these coefficients sigma or sigma tilde I. Okay, so let's make some examples. So I want to look at again at this matroid, right? And this is already the zonotope corresponding to, so zonotope of this arrangement. Okay, and I want to claim that in the coefficients, in the computation of the coefficients, there's already some kind of recursion formula. So what we want to do, we want to compute the volume, and we want to compute the areas times the normalized angles, the boundary, like this. We need to use different colors. Like this. And we want to have a simple way to compute this, so why not try to recurse? So let's say we want to delete this element. So this is an element E that we want to delete. How do we decompose the coefficients? Well, so if I delete this element, then I am left with a zonotope that looks something like this, right? Okay, so you see that already, so could draw this again. I could draw, oh sorry, I should have this, done this red, and then here's something in orange, and here's something else in orange. But then I have made a defect, and this defect corresponds precisely to the deletion of this plus the dimension shift, right? So the deletion you can think of as a projection of this along the projection of this zonotop along E. So this gets you to something, to some line segment. So you have some volume component and some boundary component. And this, if you shift it in dimension, this precisely corresponds to this part and to these parts here, right? So these are precisely the parts that are missing now. Oh, yeah, that's a good idea. Okay, so let me phrase this in the words that I will use later. So the characteristic polynomial is what is called a Tat-Grothendieck invariant. And sigma, this coefficient sigma tilde, they are almost a Tat-Grothendieck, right? So almost Tat-Grothendieck. Why do I not have directly this recursion formula? Well, if I do a projection, then in a naive way to say it would be that these segments are no longer unit length, right? A more structured way to say it is that while this might be my standard convex body that I want to use, the projection might no longer be my standard convex body I wanted to use for the projection or for the contraction or the deletion of the arrangement. Well, so this contraction here, this corresponds on the level of arrangements. It corresponds to just restricting to a subspace. On the level of zonotops, it corresponds to projecting along a subspace. Zonotops are convex Minkowski sums of line arrangements. And for me, I work with zonotops and more general with zonoids, right? So with some things that are obtained as a limit of zonotopes. Okay, so for me, zonotopes are the simplest to explain. These are the ones that I use for hyperplane arrangements, and zonoids I need to use for C arrangements. So this is just I want to say that at this point that there is a flavor of this deletion contraction relation, but it's not quite a deletion contraction relation yet because in the way I project these things, they are not the canonical convex bodies that I wanted to use. Here, they are no longer the canonical convex bodies in the projection. Okay, so at this point there's nothing canonical. So let me give you another aspect of this fact, and this will give us an idea how to find canonical convex bodies. Okay. Okay. Let me write this here. This is a second caveat. So ultimately, what I'm interested in are matroids, right? So the way I choose my convex body should ultimately not depend on the matroid, right? So if I tell you study two lines in the plane, then the convex body that I come up with and that the Mark might come up with should be the same. And in particular, the coefficient sigma tilde, they should be the same. So let's say we study this arrangement, we study this arrangement. Combinatorially, they are the same. Let's say this for specificness, this is pi divided by 4. But if you work out the sonotopes, then in one case, you would come up with this sonotop. And if I'm correct, this should be just volume square root 1 over square root of 2, right? So this should be the coefficient should be now 1 over square root of 2. And the other ones are the same, 2, 1. And in the second case, I still have the ones that we already worked out. Sigma tilde is equal to 1, 2, 1. Okay, so for the same matroid, I obtained two different arrangements, and I obtained two different Whitney two different sets of vectors sigma tilde. Okay, so this means that I have to come up with a way to define a canonical convex body or canonical sonotope that is independent of my arrangement. So one way to do this, I argue, is measure concentration. So let's say we want to realize them these arrangements uniformly at random among their combinatorial type. So for this, I parameterize them by their normals. Okay, so my arrangement is for me encoded by its normals. So I could just say, okay, I choose my first normal for this arrangement uniformly at random. Okay, and then I choose my second normal uniformly at random. So this doesn't help me a lot. But now I use a simple trick, and this is I don't choose them uniformly at random in R2, but I choose them uniformly at random in RD. And where D goes to infinity. What happens is that, okay, so my first I cannot say anything about, but what happens to the second vector? Almost perpendicular. Okay, so this is good and nice, but now I run into a problem when I want to study more complicated arrangements. So let's say I instead look at a system of vectors x, y, z, and I say my combinatorial condition is that they are coplanar. Okay, so this is a matroid which is an arrangement which in every realization spans a two-dimensional subspace. So I'm of rank 3. Sorry. So I have a matroid of rank 3, but somehow now I still want to use the same trick, and I want to just embed this into high-dimensional space. Okay, so I embed this into RD, and as D goes to infinity. Okay, so what happens? So the first, I do the naive random model, right? So I choose first the random variable, the vector corresponding to x. Then I have my random variable y. But then I have a problem because I have the combinatorial condition encoded that z is dependent on x and y. And it's dependent, the dependency is rather strong because I only want to say that these are in common two-dimensional subspace. So z has a problem. Okay? So how do we remedy this? How do we repair this? Well, we could try to make what we ultimately have to do is to make this vector corresponding to this random variable corresponding to the vector z more independent, right? So the philosophical statement is that if we have a random variable, like these coefficients sigma tilde, that depend on many sufficiently independent random variables in a Lipschitz way, but this is not so important for us at this point, then the random variable will be constant. The problem here that we have is that these variables that we have, we can make them sufficiently many by just embedding them in a high-dimensional space, but we cannot make them sufficiently independent like that. There's a combinatorial constraint here. So I claim that we can circumvent this combinatorial constraint in a clever way. So this is the following. So let's say we have an x, and we have a y, and we finally have a vector z. And there is some asymmetry here. So there is some order in which I choose my vectors, and I want to modify this vector z in such a way that I first of all recover some meaningful information about the matroid, but make this vector z more independent. So what I can do, I add an auxiliary vector for z, and this will be my first auxiliary vector for z. Okay, so if these lived in a two-dimensional subspace, this is a new vector. You can choose them uniformly at random in RD, so this will span a new subspace. Now I can do this again. I choose a second vector, again for the same vector, auxiliary vector AZ2. And then I choose an auxiliary vector AZ3. And this I do again and again, up to an auxiliary vector AZ. Let me choose it. Let me say the coefficient I. Okay? So now I want to modify my arrangement, right? So now I didn't do anything to decrease the dependence here. So what I do is I delete my vector z. Okay? And I added a vector z prime. This new vector, it should depend on the old vector in some way. So z prime should be in the span of z and the auxiliary vectors. Okay? And this is the only condition that I want to add. Okay, so here's a new way to choose a replacement vector for z. I add some auxiliary vectors uniformly at random, and then I add a vector z prime that replaces my original vector z, my original dependent z. No. These are, sorry, I can only draw two-dimensional, but these are new planes, right? So these are, so this is, you think of this already living in a high-dimensional space, okay? And now you choose these auxiliary vectors uniformly at random. Okay, and now you choose z prime according to a clever distribution in the space in the span of the original vector and the auxiliary vector. Okay. Yeah, precisely. That's you can see. I mean, rotate only makes sense if you have. I mean, if you have a codimension 1, but it depends on what you mean. So it's not cool. Yeah, so you have to be careful what you mean by that. So let's just observe two things. So first of all, let us observe that this operation kind of keeps the same matroid. So why is this not a trivial operation? Why don't I lose everything about my matroid? Well, so with probability 1, the original arrangement can be recovered from the modified one. Why is that? Yeah, precisely. The second observation is that while I had while Z was somehow very dependent on the random variable xy, I no longer have this property if I look at my new arrangement, if I look at my new vector Z prime. And this is rather clear. Well, I'm in the span of Z's, but these are auxiliary vectors. Okay. So there is already something, and now I miscalculated the time, so I have to improvise. So let me just try to give you an intuition why this ultimately leads to a proof. Okay, so let me describe how the proof now goes. The problem is you have to go to, somehow you want to use measure concentration, and so the number of auxiliary vectors that you add for every relation that you want to make less dependent on the other goes to infinity. So you have a sequence. So, yeah. Sorry, I thoroughly miscalculated how long I would need. So let me describe how the idea of the proof, and let me then go over the steps. I still won't need the whole time, but okay. So idea: define a sequence of arrangements. And here I should be actually more precise. It's a probability spaces. More precisely, probability distributions on arrangements A of k such that, well, with high probability, with high probability, the characteristic polynomial of an element in this probability distribution coincides with the characteristic polynomial of the original arrangement up to a constant depending, or up to a function depending on k. And the second step that you want is that the sigma tilde vectors of these of the zonoids associated to these arrangements. Yeah. Yeah, let me actually. So asymptotically they're very close. Okay, so asymptotically they are the same. Okay, up to a correction, asymptotically they are the same. And the second property that you want is that the sigma tilde, well, up to an error that goes to 0, they satisfy the following recursion relation without an element. Sigma tilde. Deleted an element. Okay? So in particular, the sigma tilde of Z of this arrangement is Tat-Grothendieck invariant. Invariant almost surely. Okay, so this means that while before we had these pesky terms in our recursion relation that corresponded to volumes, that corresponded to the fact that we didn't have a canonical candidate, now I have a way to produce arrangements which, okay, so these are not quite canonical convex bodies because their dimension goes to infinity. So the rank of this arrangement diverges. Which means that in particular the associated zonotopes and zonoids, they go to infinity in dimension. But what I'm saying is that these sigma tilde coefficients, they still behave in a controlled way. And now you have to think about it. So you have to be careful at this step. So you have to think about it that you now have a canonical convex body, but it's a sequence of convex bodies that behave canonically in terms of these coefficients sigma tilde. Okay, so the projections no longer depend on the individual terms. Okay, and this is why in the end you can verify that while you here had some additional terms, you have this relation, this Tadrotendick relation, this division contraction relation in the end, without any factors here. And now you have to just last step, verify that that these sigma tilde coefficients now coincide with the coefficients of the characteristic polynomial, well, for the only basic case, right? So you have to only verify that sigma tilde of z of, well, let me write it like this, the line to the k coincides with the characteristic polynomial of a line. And then you're done. Actually, with so you have to, it's minus lambda here because you have to account for the factor. But that's it. Okay, I'm sorry, I thoroughly miscalculated the time, so I didn't prepare beyond this. But maybe you can, maybe you can ask questions and I can answer them.